let's get started. So last time we start learning how to draw Feynman diagram. So last time I missed the lecture note. I missed this factor. So you need to integrate out this internal point in position space. The last time I missed this factor. Integral. I'm very sorry about it. And then this is the moment, position space and the momentum space are down there. Yeah. So, and also, if there is a bubble, vacuum bubble, and then this is Feynman rule. So I just give a rule just now, but later, actually, next lecture I will give some example to apply this one. But today I'm going to talk about the scattering amplitude and so on. But next lecture I will give example to use this rule. So just wait for a moment how to use these rules. And then so there's a vacuum bubble. So last time we have the vacuum bubble, whatever 8 or anyway. So you guys already did my difficult homework, so and then you use this kind of stuff right already. This kind of stuff I already asked during the homework, so you already get familiar with this vacuum bubble. And then since we have this this one, if you apply this rule, since all the momentum here is conserved, so they always appear something like this one divided to the force. This leads to the factor delta the 4, and the pitch can be understood as the volume of space-time. The volume of so that's one problem. So, and also there's an issue about the time integral. So we can talk about the time integral. The limit is so this I epsilon is shifted to get the vacuum. Through vacuum. That's what we did to the place where the something like so this is Z, and then whatever P1, P2, P3, and P4. You will get this kind of integral. And the question is how to deal with this I epsilon. Because if you have I epsilon, I think okay, yeah. I epsilon, so if you multiply I epsilon minus I epsilon you get the let's see, minus epsilon, right? Epsilon times infinity. So either t goes to infinity or minus going to infinity, this part is problematic. So that's the issues because the exponential blow up. For instance, e to the infinity minus I times minus I is equal to minus, and then t times epsilon. And if t goes to minus infinity, this goes to infinity. So that's one problem we have. So this is going to be the divergent problem we have. To cure that, we will do the make change of variable. But in that case, we only focus on first this part. The time integral is so the rest of part is okay. So what we need to do is that the limit epsilon goes to 0. Let's see. Sorry, I think first I focus only first part. Sorry. First part, this part. This part. And then t. Okay. Then I will make the following change of variable, z0 tilde is equal to z0 1 minus I epsilon. This kind of change of variable. Then the integral will be limit epsilon goes to 0 plus t minus plus t and minus t is z0 tilde e. And then there's a measure, there's a Jacobian of this one, is 1 minus I epsilon. Okay, so this is Jacobian. And then what we need to do is that the e to the minus sorry, I think I'm wrong. It should be plus. It should be plus, right? Sorry. So what I did is this should be dz0 tilde is equal to, in fact, 1 over 1 minus I epsilon. And the epsilon is very small, so therefore, if you do the Taylor expansion, you get the 1 plus I epsilon. So this is plus I epsilon. So there is a typo in my lecture note. And then so here minus I sum of p0. I think it's full of typo in here. So just plot down into here. Yeah, so I think there's a full of typo in here. And z0 tilde 1 minus I epsilon. Okay, so this is the case. And then we define p0 tilde is equal to okay, so I think this is okay. P0 tilde to be 1 minus I epsilon. What I'm doing here, I think it should be okay, right? So far it's okay. Everything's okay. And then what we need to do is that I got confused. P0 tilde P0. Sorry, I'm just disorganized. now. Its limit epsilon goes to 0. D0 to the 1 plus I epsilon. And what I want is what? So far it should be okay. E to the minus I sigma P I 0 tilde Z 0. So I think I should write down this bigger. So I got confused. It's different from what I have written in the lecture note. So Z0 tilde is this guy, and Z0 is just plugged up for me. So far it's okay.
This should be a distribution.
Sorry?
Z0 divided by 1 minus I.
Is equal to P naught.
The line above, there should be a division. Z0
Divided by? Does it work? Ah, you're right, that's why I made a mistake. Oh, sorry. Sorry. So my lecture note is correct, sorry. I didn't follow, sorry, thank you very much for helping me. Sorry, so Z0 tilde is equal to Z0 over 1 minus I epsilon. Sorry, my brain is not working. So if you plug in T, Z0 is T times 1 minus I epsilon. This factor cancels with this factor. Then it becomes plus D and minus D. So therefore Jacobian is 1 minus I epsilon. That's okay. And then thank you very much for helping me. And then sorry. So here thank you very much for helping me. So like this way. And then, so I think the lecture note, there's a typo here, there's a tilde, but that's not true. And we define if you define like this way, this is equal to limit of epsilon goes to 0, t minus d, d0 tilde, 1 minus I epsilon, this is just become 1, and e to the minus I, sum of p0 tilde I, and then z0 tilde. Okay. Do you agree with that? So I think everything up in this is, sorry. So at the first lecture, sorry, my brain is not working. So now, if you plug this one into here, minus 1 I epsilon, minus 1 I epsilon cancel. So that now we have a desired form. So t to minus d and p0 I tilde times z0 tilde. Okay, is it okay? Do you agree? So this, since epsilon is very small, this is, if you roughly speaking, p0, 1 plus I epsilon. Okay. And so recall that when we do so the final prescription, when you have the propagator p square plus, minus m square plus I epsilon, and this I epsilon really coming from just shifting the p goes to 1 plus I epsilon. Okay. So when you do the p0 square here, but if you shift p0 plus 1 plus I epsilon, of course this epsilon and this epsilon is slightly different because there's a factor of 2 up here once you do the square. But to get the epsilon prescription, this is consistent with the shifting p0 momenta to a little bit plus I epsilon. So this is consistent with the epsilon prescription. So this to get this so to get the vacuum, so originally our motivation is that the so this I epsilon description is just omega and limit t equals to infinity 1 minus I epsilon, and then here there is some overall factor e to the minus I e omega t, and then there's a factor, I think this is the omega 0 inverse, and then e to the minus I h naught t minus t naught. So this I epsilon is originally motivated to get this true vacuum from to try to relate true vacuum and then the vacuum of free theory. And then once you introduce minus I epsilon, so the other term omega 0 e to the minus I e n n t, this kind of term will be negligible by comparing this factor. That's our first motivation, to introduce this minus I epsilon. But if you treat this time integral like this way, it's consistent with the minus I plus I epsilon prescription of Feynman property. Do you understand what I mean? Is it okay? So when you do that, p squared is equal to p naught squared minus pi squared, right? That's I summed over. And when you shift to p naught like this way, it automatically generates this plus I epsilon. That's what I mean. Okay. So that's the issue of this this integral, time integral, and we try to interpret this infinity volume issue from now. Any question at this moment? And then please always look at the latest lecture note. So here there's a typo here, but anyway, I will correct later. Okay, now we try to understand what partition function means. So that record, as we record, so there is a factor of the vacuum. So this is partition function of the theory, which is 0 time ordered e to the minus I hi dt. And like this, is it minus I? I didn't print out this part. Yeah, it's okay. dt, and this is equal to exponential. Last time I explained this vacuum bubble plus this kind of stuff. I'm sorry. And so on. So that's what we learned last time, and then we try to interpret what it means. Okay. So we know that the so we just consider 1 is equal to, so I already, where did I write? Oh yeah, here. So if you take the inner product of the true vacuum, what we have is just this one, limit t goes to infinity 1 minus omega 0 square e to the minus 2 and e to the am I doing correctly? Sorry, I think I have written something wrong. No, it's okay. Oh, it's okay, it's okay, sorry. So here, something wrong here is, this is good Hamiltonian. Sorry, so this is not 0. And then, so this is equal to limit of this factor. And then you can introduce here is e to the I h naught t minus t naught, because h naught is the eigenvalue of 0 is the eigenstate of h0, which and the eigenvalue is 0. So therefore, even if you introduce this one, it's just 1. And this factor is actually u. T and t naught 0. So that's the so this factor is this equal to. And if you take the inner product, what we get is that the most likely, I think I need to do again do the typo in my lecture notes. E omega 2t, it should be 2t, and then 0 u t and minus t, and that's what we had. So therefore, if you look at the partition function, so this factor is equal to u t and minus t. Okay, do you understand? Is it okay? Sorry, my brain is at the beginning not working. so this factor is partition function. So therefore, what we have is the partition function is equal to limit of t goes to infinity 1 minus epsilon, which is the 0 u t minus t 0, and the limit t goes to infinity 1 minus epsilon, and then omega 0 square e to the minus I infinity to t. Well, that sounds a bit strange. Let me check my calculation. So this n times it should be no, I think this should be plus, and this should be okay. So factor of 2t is missing. So therefore, so if you take the taking log of z, so log of z, and this factor is finite. And if you take this log, essentially what we get is minus I e omega times 2t plus limit infinity 1 minus I epsilon minus I e omega times 2t plus whatever log 2 anyway, so square term, and this is finite. Okay, this is finite, and this is so t goes to infinity means that this term is divergent. Okay, when you go to t goes to infinity, so therefore e omega is the limit t goes to infinity 1 minus I epsilon to t I log of z. So when you take t goes to infinity, this term is negligible comparing to this term. So this term is dominant. Okay. And if you take the ratio between 2T and log Z, what you get is the vacuum of the true energy. Okay. And to get the vacuum energy, so to get the vacuum energy, we can divide. So this is the energy of the true vacuum. So the vacuum energy density is E omega is B. B is the volume of space-time. Okay. So to get the vacuum energy density, so you have to divide by the volume of space-time. So then this is equal to limit of t goes to infinity 1 minus I epsilon I over 2 TB log and z. And we know that the log z is essentially, so z is equal to exponential of this vacuum bubble. Okay. So therefore this is equal to limit t goes to infinity 1 minus I epsilon I over 2 t b, and then you have vacuum bubble plus dot. And we know vacuum bubble has this factor Vt, okay? But that cancels with the distance. So therefore energy density is well defined. Is it okay? Do you understand?
It may still be divergent.
What?
The energy density, because there are so many diagrams, order by order.
Order by order?
So we have a lot of diagrams. So will the vacuum energy density be divergent?
Why? If you sum over?
Yeah.
But the first order is only one, this one. The second order is only these two. And you already divided it, so if coupling constant is very small, these contribution very small, right? That's what you did in homework. That's what you did in homework. Okay. Anyway, so here we care about so-called IR divergences. So this B times T, so it's coming from the volume of space-time, and then here we care about the IR divergence. But there's some issue about the UV divergence, which is P goes to infinity. So that's called UV divergence. So this issue will be treated in other renormalization in coming due courses. So you have to wait how to deal with this UV divergence in the later lectures. Any question? So here I cure two issues. So one is this minus I epsilon time integral for this minus I epsilon issue. And then second issue is this divergence of space-time for vacuum bubble. So if you divide by space-time volume, you can cure this IR divergence. Any questions so far?
Why is it called IR divergence?
I mean, why is it called IR divergence? So here, so this integral essentially what we have is the e to the fourth, e to the I, p, z, whatever, minus, maybe minus, limit, p goes to 0, right? P goes to 0. This integral is essentially coming from p goes to 0. So this is the delta of, so limit, delta p, right? Up to normalization. P goes to 0, right? So maybe 4 here. So P goes to 0 means IR. So momentum goes to 0 means IR. So momentum goes to infinity means the UV. So that's what. Any question so far? Sorry about here the confusion. My brain is not working. Okay. If not, so the application I just give Feynman rule just now, but the application Feynman rule I will explain the next lecture. For time being, I will talk about so-called scattering theory and S matrix. Today, my plan is to give the scattering amplitude and S matrix. Okay, scattering. So I create one section to remind yourself of what is the scattering theory of quantum mechanics. Maybe I'll get you bored if you already learn it. But anyway, so there's a word called repetition is a mother of learning. So even if you already learn, you can repeat it, learn several times about the same thing. So scattering process is essentially scattering process is essentially there's a particle is there's a particle and there's some scattered by if you put this is exactly what Rutherford did. I mean just how to say. Insert the alpha particle to the gold foil, and so he just measured how the alpha particle is scattered by gold foil. That's how the quantum mechanics is actually developed. And so therefore, so this scattering theory is really the intersection between theory and experiment. So therefore, it's very important. So that I'm just trying to remind yourself, this is not written in Pesky and Schroeder, but I just remind yourself of the scattering theory of quantum mechanics. It's at just a very, very low level. It's already non-relativistic. So, but I just try to, if you don't learn it, it's okay. But if you can learn it newly. But if you already learn it, you can just refresh your memory, review what you did in when you're undergrad or whatever when you take quantum mechanics. So the Hamiltonian of the free theory in the quantum mechanics is this guy, and of course the eigenfunction is what? Eigenfunction of this one is what? E to the I ikx. Okay, I think I should use ipx. Is it okay? Oh, okay. So let's follow my lecture. I think it's better that you know to make it. So this is the eigenfunction, so everybody knows. And then so the eigenvalue, so the h naught acts on k of x is equal k squared to n. So therefore, there's a two eigenfunctions. So this minus k is also have the same eigenvalue. It's super super easy. Everybody can. Oh, sorry. I think yeah. Minus k also has the same eigenfunction, eigenvalues. But also you can just have a superposition or linear combination of these two. So the so one is the k0 is equal to cos kx, which is just e to the I k. Maybe I will get you more side over 2. This is the even at the parity, so the parity transformation P is x goes to minus x, and P psi x 0. And then is sine kx and linear combination of these two. And then parity transformation, under parity transformation you will get this. So that's everybody knows. So that's everybody knows, super easy. And now we will add some potential to the Hamiltonian. I think these are too easy for you. But let's do that. Easy. So then, now let's add the potential B, which it takes the following form. Oh, I think potential minus x naught, and the potential is something like this way. So let's consider the Hamiltonian, which is p squared plus 2m plus b of x, and b of x is written here. Okay, let's add it. And so we know that so if there is no potential here, it's just a plane wave, e to the I. Let's call region 1, region 2, then region 3, and at region 1 and 3. So the wave function should be written as eigenfunction for Hamiltonian should be written as follows. So this is region 1, and then C e to I minus I k x, this is region 2. Okay, so that should be the form of the eigenfunction for this Hamiltonian. Is that okay? And then we can treat as A is this some kind of a wave function that is incoming, ik, the k. This is the amplitude of the incoming the wave, and B can be understood as the outgoing. Okay? The amplitude reflected wave. So the wave just hits on the potential and coming back, right? There's a possibility. That's the meaning of B. Likewise, the C is like this way, okay? And then D is the so be careful with the direction of the arrow, okay? So that's the interpretation. And S matrix, I think as you learn in quantum mechanics, it's just related B, C, and AD. So of course, this S matrix means that the A is reflected to B, or D is just a, how to say, surpass this potential by quantum mechanical process. So therefore S11, S12, S21, S22. Okay. So this is S matrix. The relation between this amplitude is S matrix. That's how originally introduced in quantum mechanics. And furthermore, one can just consider the following process, scattering process. Maybe I should yeah. So psi plus of x. So first we consider that all the wave is coming from region 1. Wave function is coming from region 1, and A is either reflected to B or it just goes, how to say? The surface this potential barrier and it becomes C. So therefore, one can consider the following. So you just ignore D. In this process, you have ikx and plus B e to the minus ikx and then C e to the I kx. That is region 1 and region 2. And then, so R, so this is called reflection coefficient, is called B over A. And then T is transmission coefficient, which is called C over A. And of course, the all the amplitude should be, how to say? The probability should preserve, so A over B is the probability which is reflected. Or the C over A is the transmission probability. So therefore, R squared plus T squared should be equal to 1. Okay. So that's already we know. It's super elementary. And I think I should put this one into up. Is it easier to read? So this is the how this S matrix appear and the refraction transmission amplitude appear in the quantum mechanics. So I just remind yourself, you guys already learned this kind of stuff, right? In quantum mechanics. It's not bad idea to learn it again. Okay. And now, so we consider the following: so we know this linear combination. We know this linear combination here can be understood as the following: the phi naught is equal to cos kx plus theta naught in region 1, and then phi naught is cos kx minus theta naught, and then x. So this is region 3. Sorry, I think. Did I make a mistake on the no? So I think this is region 1. According to my lecture note, let's believe I have written what's the correct thing. And sine kx say 1 region 3, and psi 1 is sine kx region 1. So let's consider the following thing. Okay, and then let's do the computation. If this is the case, what is the scattering amplitude? So So if this is the case, what is the A and B? Here, for psi 0, what's the? So here, okay, let me write down the yellow check or yellow, mini yellow. So here it should be A should be e to the I theta naught, and this B should be not A. So this is region 3. So the C should be and D should be e to the minus I theta naught. Do you agree? Maybe more strictly speaking, divided by 2. Divided by 2. But I don't care about this kind of normalization. Do you agree with that? If you plug this one, you get the cos kx plus theta. Okay? And here, region 1, this is equal to A, should be e to the minus I theta naught, divided by 2. And then, what was that? B should be equal to e to the I theta naught divided by 2. Okay? So, okay, and plug this one into there. The S metric should be something like e to the 2 times I theta naught times 1 1. Do you agree with that? Because do you see that? A and D is e to the minus I theta here. E to the minus I theta. And B and C are e to the I theta. So therefore, if you multiply e to the 2 I theta to the A times D, you get the BC. Do you see that? Is it okay? Okay, some students are not following. So AD is essentially minus I theta naught. I don't care about the overall coefficient. This is AD. And this is the S matrix, and the BC is e to the I theta naught, and e to the I theta naught. Okay? So therefore, S should be that one. Okay? So, are you following? Okay? And likewise, we can do the same game. So here, I don't care about the overall coefficient. This should be means C should be equal to, what was that? E to the I theta 1, but D should be equal to minus e to the I theta 1 to I and to I. And this one means mention A is equal to e to the, what was that? I theta 1 and minus, is it correct? Yeah, over to I, and B should be theta 1 over to I. Am I correct? Sorry, minus sign, sorry. Okay, so therefore, scattering amplitude should be e to the 2I theta 1 and 1 1. Do you agree with that? This is scattering matrix S. Do you agree? Do you agree with that? Sorry, I'm also tired, and you guys are also tired, I guess. Okay. And now, so we try to write down this, so this phase shift. So scattering amplitude can be written as a phase shift. And also we will see this reflection and transmission coefficients can be written in terms of this phase shift. So now, psi plus why do I pick this? So I picked A as the, oh yeah, now that's not what I mean. Okay, I think it's a linear combination I take. So linear combination given parity, let's see. Oh, 6 1. Parity. So we take the psi plus e to the I theta naught, psi naught, I times e to the I theta 1 psi 1. So I just take this linear combination of this this psi naught and psi 1, and then here we take the e to the I kx plus 1/2. Sorry, what I'm doing? It's very strange. Oh, I see. Okay, so the way I have written is very misleading. So here, this should be region 3. Sorry, this should be region 3. Sorry. So my lecture note should be opposite. Sorry. So region 1, we have e to the ikx plus 1/2 e to the 2I theta naught minus e to the 2I theta 1 e to the minus ikx, and this is region 1. And here A is 1, is normal as 1, and C, B is equal to this one. And C is chosen to be like this way, e to the 2I theta naught plus e to the 2I theta 1 e to the I kx, and this is region 3. So this is the only combination, this combination of the phase is the only combination that will kill D. So here D should be 0, right? Here D should be 0. So therefore, I just pick the combination of psi naught and psi 1 in such a way that it kills the D coefficient. That's what I did. Do you understand what I mean? So D should be 0. So therefore, when you take a linear combination of psi naught and psi 1, so you have to. So what I did is that let's go alpha times psi naught plus beta plus psi 1. And indeed, I pick alpha is e to the I theta naught, and this is equal to I times e to the I theta 1. I pick this one. Then D will drop out. Okay, drop off. So that's what I did. And then this combination automatically determines region 1. That's what I did. Do you understand what I mean? Okay. So now we can compute refraction and transmission coefficient in terms of phases. So in terms of phases, so R should be, I know, so what, A is equal to 1, so therefore denominator is just 1. So therefore we just need to read off B and C. So R is just B. B is this guy. And T, transmission. So this can be understood as the it's the way you write. I don't know why I have written like this. This is the traditional way to write down. Minus and sum over is equal to 0, 1. Okay. And also here we can just write down like this way, 1/2 e to the 2I theta naught minus 1 plus e to the 2I theta 1 minus 1 and plus 1, and this is equal to 1 plus sum of, I'm very sorry, this, yeah, it's okay. L is equal to 0, 1, I times e to the. So that's the reflection transmission coefficient, and then everything determined by this phase shift of this eigenfunction. Okay. So the S matrix can be written as this phase shift, and also reflection transmission coefficient are written as the phase shift. And then now let's look at some particular example of the B, which is delta function. I think many students already go through this exercise, but it's okay. I mean, it's just yeah, repetition is mother of learning. Let's consider the delta function. G can be either positive or negative. Okay. If it is positive, it's the attractive potential. If it is negative, it becomes repulsive. Do you understand what I mean? So if it is positive, the potential is just a delta function like this way, right? And this G is greater than 0, and if it is negative, it's just repulsive. G is like this way, repulsive. So now, so we will do that. So then, you can just solve the, so first we impose, so there is something strange happen at the origin, only x is 0, due to this delta function, okay? That we already can expect. So we need to impose the continuity of wave function. So that's the continuity of wave function. And you can. So here we have the Schrödinger equation is something like a nabla square. Okay, delta ddx square 1/2m. Psi of x is equal to this potential. Sorry. Minus 2g delta x. And then I think there must be minus sign here. So that will give you so this is Schrödinger equation, and then you just need to integrate over. So you just need to integrate over minus infinity dx, and this will give you the condition that the d psi naught minus minus 2k which, sorry, okay, so that's the Schrödinger equation would provide us. So if you, I think, let me think. Oh, I think here I normalize m equal to 1. Sorry. Yeah. I'm very sorry. I just be sloppy about coefficient. I think I ignore 2m. I think here I ignore 2m. So I drop this part. Then does it make sense? So this integral will give you 2g times psi naught 0. And then this integral will give you, so minus infinity to 0 plus and 0 minus to minus infinity. So therefore that will give you this factor. Okay. Do you agree? Is it okay? Are you guys following now what I'm doing? Is it okay? Good. And then now I just plug this solution. Let's see. Here I assume the so the parity is the even one. So I just picked the side takes this kind of form. Then what we have is this is equal to minus 2k sine zeta naught, and this is equal to minus 2g zeta naught. So therefore this will give you that the tangent zeta naught is equal to g over k. So the phase of this wave function is determined by the momentum and the coupling constant g here. And if you just manipulate this one, and then this is equal to e to the 2I zeta naught is equal to 1 plus I tangent zeta naught 1 is equal to k plus ig, k minus ig. Okay. So this is the S matrix of this even phase, parity even. Okay, this is parity even. So we already knew that the S matrix is determined by phase. And if you, for odd case, there's so for odd case so here what we saw is that essentially the wave function takes the following form. So the sine naught of 0, and then here x, and then so of course there's discontinuity at the origin, but here essentially you have something like that, whatever. It's hard to draw, like this kind of wave. So this is what's really happening. The wave function will become like this. You understand? So the derivative of 0 minus, what was it? 0 minus and derivative of 0 plus is, of course, there's a difference. That is given by the wave function body of sine naught. That's what it. So therefore, wave function is it's continuous, but the derivative should be discontinuous. Do you understand? Okay. So therefore, the wave function takes this kind of form. However, for odd one, for parity odd one, it always, by definition, sine 1x should be equal to 0. Okay. Otherwise, it cannot be odd function under the parity. So therefore, it should be coming here. So therefore, it should be ordinary sine wave, like this way. So therefore, this means that the theta 1 should be 0, and the 2I theta 1 is equal to 1. So it's super easy for odd one. Okay. Okay, so that's what's really happening for scattering amplitude in quantum mechanics with the auto function potential. Okay. And then we will try to, make this kind of theory to a relativistic one from now. But before that, we try to analyze what this means. Do you guys learn this story during the quantum mechanics, or? Okay, good. Okay. So suppose that the k, so here we assume that the k is the just real number, but no one prohibits that the k can take the complex value. K is equal to k1 plus ik2. Okay, good. Okay, 普段 physics education is not that bad if you learn this one. I don't know, some other graduate students even do not teach this kind of stuff. So, but if you learn it, it's okay. Okay. So, and suppose, so here, if you have suppose the k takes the complex value, and of course, if S matrix, this guy. So I mean, this one is too trivial. This one is too trivial. But if you look at this one, this S matrix has a pole. At k is equal to ig. K equal to ig. And let's look at what it means. If you plug this one into here, the k equal to ig, this is minus g times x. But however, region 1 x is less than minus x naught. Okay? And this region 3 x is greater than x naught. So minus g times x, and x is negative. Okay? So therefore, if you go to the far minus infinity, this part becomes divergent. Okay? So therefore, a should be 0. We need to normalize, so a should be 0. A should be 0, and then so B is can be non-zero, and then C and D. Let's see which one should be 0. Minus. So this, if you plug down into here, G times X, right? So D should be also 0. D should be 0. So here, I'm assuming G is positive. And here, so if you plug this one to the Hamiltonian of this one, energy, BB, is equal to minus G squared over Tm. Okay. So this has a negative energy. So here, what we saw is that essentially, the potential is essentially equal to something like a potential is delta function, an attractive delta function potential like this. So therefore, wave function can have, and if you plug this value into here, wave function takes the following form, something like this way. Yeah. I don't know. I mean, it's sorry. Wave function takes the like this way. That's a form of wave function. So therefore, this state is trapped into this attracted by this delta function force. Therefore, this can be understood as a bound state. So here, bound state usually means that if there is a okay. So in general, so let me, I think I can erase here, right? I already, I just want to keep this wave function solution. So usually, so if there's some potential V of R, and there's an X R, and if the potential is something like this way, let's consider this kind of potential, R. And this can be understood as some the potential of the whatever, the nucleus, and then the bound state is always like appear in the negative energy, which means that it's trapped under the potential, and the wave function takes the following form. So that, of course, bound state is something like this way. Oh, sorry. And then like this way. Oh my goodness, my drawing's horrible. Like this way. So these are called bound state. So it's trapped in a trap. The bound states. So now for generally means that no longer I assume the potential is the delta function. So it can be any like potential. Generally, the pole. If you analyze the analytic property of S matrix, we can conclude the following. So the pole with of S matrix with a positive imaginary value. Okay, maybe it's better not to write. I already written down in the directional, so I just write down only the k phase. So the space of momentum, and this pole on the imaginary positive axis. If there's a pole in the S matrix, these correspond to bound state. So as we saw, when k is equal to Ig, we have this kind of bound states trapped in this attractive delta function potential. And this is also true that for general potential V. And then physical like how is it, scattering? It's called scattering state. So the physical scattering states always appear scattering states, or maybe physical. Scattering states always appear on the real axis. So this is the axis. But there is sometimes there is some states appear around here. That's called resonance. It can have the negative imaginary value and the positive. Negative imaginary, it has the pole at the negative imaginary value and a non-trivial real number. Okay, and that corresponds to the resonance which appear around here. It has, since it has the positive the positivity, non-trivial real number. So therefore, the energy is the positive. But wave function is resonant around here. It's hard to draw. And here there's a tonal effect, and there is some small amplitude can decay to infinity. So that is called resonance. Resonance means that around here, wave function is really fits into this potential. That's what it means, a resonance. Here, this part is resonance. And then this orange line, scattering state, is really upward. So here, of course, there is a scattering state. That is super easy. These are scattering states. Scattering. So that's, if you analyze S matrix, the analytic property S matrix, one can see that what kind of states the system has. Okay. And if you look at if you analyze the analytic property of the S matrix, we can just distinguish what kind of states you have. Bound states, resonance, physical scattering states, and so on. Did you learn this kind of stuff in undergrad? I hope so. And in particular, so if you look at the resonance, so in general, this resonance S matrix will take the following form. So E minus ER minus I gamma over 2 E minus ER plus I gamma over 2. Essentially, just write down this one. Essentially, what I did is just write down this kind of S matrix in terms of energy, not the momentum. And then what we have is essentially, so here S can be written 1 plus IT, and then sigma cross section. I'm going to explain why this should be the case. So this cross section is proportional to P square, and the gamma, so that is gamma square E minus ER square plus gamma square over 4. And this is called Brett-Wigner formula. And then if you look at this kind of, let's see, this is E, and this sigma, it forms like this way. And the roughly gamma is around here. And in fact, so the resonance states, the lifetime of resonance states, lifetime resonance states is the wave function stay in this potential. It's a lifetime of this resonance, and but it by quantum mechanically it transmitted into this Argos infinity region. Okay, so therefore the states, the particles stay in this region, but it just can decay to infinity by. So therefore, and this formula will tell you that the lifetime of this particle is tau is 1 over essentially gamma. So this is lifetime of this resonance state. Sorry, lifetime of resonance state. So if you analyze this kind of like a scattering matrix, one can learn lots of property of the states and the particle. Okay, let's take a break. Just go spend a lot of time. But I hope you guys already learn it. But even if you don't learn it, you now understand it. I hope. Take 10 minutes break.
Yes, let's do something out of
Since I know that if we set a phone with GFI as an for the energy.
So now we assume that the G is the what's that?
As a function of
Negative.
oh G, yeah, G is
G is negative. Then the potential is something like this. Potential is something like this.
oh yes. So that function.
So therefore, the whole can take the imaginary part. So this is the extreme example. This is delta function example.
Yes.
So that, but if you use this kind of stuff, the whole can be negative.
Yes, yes, but I do not understand how
Real part that is so real part is really about the plane wave, right? So this case, real part is so you're talking about this case. This case I will give you the amplitude of the plane wave, and this is the wave function which takes the form of with this kind of stuff. The trapped state. This will give you trapped state. This is wave function. So this means that this real part, yeah. The real part. And this part will be responsible
Okay.
But if you use delta function, you cannot see this kind of structure. So therefore, you cannot see this part. You cannot see this part. If you use delta function, but if you use the ordinary potential,
You would remember if we select the function and potential, we only found
so you need to really consider general potential to see the resonance. Yes. Just now by assuming these four functions, are we changing the basis about the? No, it's not. So one is the A-T-T-I-K-O. So this one is the so either this one or you can have the how to say cosh AX sorry, I think whichever is operating. Then if you pick this one is A is equal to E minus half theta zero and then B is equal to E minus half theta over the subject plus that. Okay? But if you choose sine AX minus theta 1, A should be equal to something, right? And these two states already, theta 1 can be this theta 0, theta 1 corresponds to N. The left hand side you have a two variable n. Right hand side you have two variables, theta 0, theta 1.
You mean the 2y and the
No, I'm talking about here, only here.
only here?
Yeah.
And the specific one single function.
Yes.
And this is not.
Yeah, so therefore, if you use alpha plus later, then so here A corresponds to alpha times this and beta times this, and then B corresponds to alpha times this plus beta plus this. So therefore, base change, just base change.
And in this space change, the S matrix will become like.
It looks much easier. So
By
S,
scalar.
yeah, S is equal to E to I theta I. S matrix becomes super simple in this space. If you use
Because here I can be 0 and
yeah. So I assume psi 0 is even or psi 1 is odd. And depending on this, the S matrix will change. So you can diagonalize. So if you use this wave function, if you use psi 0, the S matrix is diagonal. This basis, in this basis, the S matrix will become diagonal. That's why, so this base is easier to use this S matrix. There must still be one S matrix between A and C. But here we pick particular N, B, and C and D. And this one is also another N. But it's a nice basis for S matrix.
But however, if we generalize this to all the wave functions,
Yeah, then
on the
it's
left
yeah.
side, we can divide it into
two
pieces, and we calculate the
Yeah.
S matrix.
That's
Directly.
Yeah. Yeah. Okay. It doesn't change so much. Oh, that's better. That's better now. Good. So by the way, on Friday I will give some colloquium talk about quantum field theory. This is exactly I will explain my research in terms of viewpoint of quantum field theory. If you're interested, you can come. It's that topic is very advanced, but I try to explain to non-experts, to very sophisticated one. Do you guys have a class on Friday afternoon? Oh yes, it sounds. I don't know. I mean, if you guys really planning to come to my lecture, that's a colloquium. I mean, we may need to change the room indeed, because I mean, if so many students come, the room cannot accommodate so many students indeed. You can be honest, how many people are planning to come to colloquium? Not so many. Okay, then it's okay. Okay. By the way, so you can submit the homework in front, or you submit it via online. Okay, so let's talk about the non-relativistic one. Okay, so let's get started. So as I mentioned, what we are doing is essentially the same as what Rutherford did, alpha particle and the nucleus of the gold foil, and you just find how it's scattered. Alpha particle is scattered, and we can see what's happening in the nucleus. So that's what Rutherford did, and we will do the same thing. So the cross section is indeed given by number of particles. Particles scattered. Divided by unit time and unit flux. And time and flux. And the flux can be understood as the number density. in the beam times the velocity of the beam. Okay, so that's, and often people just write down like this way: number divided by times and flux. Okay. Okay. And dimension of the cross section should be is typically unit is 1 bar, which is 10 to the minus 28 meter square, and this is femtometer square. Femtometer square. And usually, so cross section, total cross section, sigma of proton scattering is about 100 millibar. Is about 100 millibar. Oh, 0.1 bar is equal to 0.1 bar.
Does this depend on energy?
I'm sorry?
Does this cross-section depend on energy?
Cross section depends on energy. No, it's about the number density and the velocity. It depends on the number density, the velocity, and the scattering particle, so that it's independent. But the number, so I think the energy should depend on the luminosity. Yeah, so the luminosity depends on energy. So therefore, so this sigma can be understood as effective radius. Effective area of this scattering object. Okay, this nucleus. So this can be understood. What was that? What I'm trying to say is what? This can be understood as the vective. Effective error, which is proportional to probability. Of interaction between target radiation target alpha particle on target radiation and yeah, so effective area of target. So in quantum mechanics, so this can be written as follows: d sigma be written dv, d phi 1/5 dp. So this, as I mentioned, this is flux and time and number. This is flux. So so here. this is probability of scattering per time, unit time, and unit volume. Okay, so this is the probability, and then B is the volume, and this is flux. And then often so this is called differential cross section. Differential cross section. Cross section. And often people are interested in the following. So yeah, and then this is equal to indeed 1 over B1 minus B2 times dP. Where B phi can be understood as the B1 minus B2 divided by B. So this is flux. And B is a velocity, so be careful. So Bi can be written as Pi divided by the energy of velocity, not momentum. So this is velocity. Velocity. And this is momentum. So be careful of the difference. So velocity, you need to divide by energy. Momentum. Okay. And often people are interested in this kind of stuff, d sigma divided by d omega. And we also evaluate in the due course this differential cross section. Omega is essentially how it's scattered. So whatever. It's hard to draw this kind of stuff, but there's a target. There's a target here, and there's a particle instant beam here. Let's use a different color. The instant beam here is coming, and then scattered to the direction. So this angle is the omega. So this instant beam and scattering radiation. In the angle. So we want to evaluate this guy. So that the ultimate goal is to evaluate this guy, and so on. And to do that, so we would like to understand the relation between this guy and the S matrix. Okay. So in relativistic sense, so we would like to understand the relation between cross section and S matrix. And to understand a cross section, sorry, to be honest, this kind of stuff, this luminosity, beam, or whatever, I think Gu Jiayin and then Xiaoding Yu are much more expert than I am, so it's better to ask them instead of me. I can explain a bit about S matrix, but this kind of experimental stuff, they are much more expert than I am. So anyway. So to construct this matrix, we have some kind of principle. So we need to impose. So here, S matrix series, general property S matrix series, that is short range interaction. And then superposition principle and then unitarity. This is equivalent to the conservation probability. And then other property is the Lorentz invariance. And then there is some additional properties. So for causality, causality and analytic principle. Causality principle, and then analytic TCP principle. Analyticity principle. They're closely related. And then analyticity, I explained in quantum mechanics a little bit. I already explained around this a little bit. And I'm going to omit a slightly. So this part I'm not going to talk about so much. But I will construct a explicit form of S matrix by using these principles. That's what I'm going to do. So this part, I mean, this S matrix theory, the explanation Pascal showed a bit hard to understand. Actually, Schwartz, I cited which section? I think 5 point something. Where did I cite? Seems like I updated. I didn't print it out. I think. Anyway, so Schwartz section something. So this one is better. My derivation is slightly different from Schwartz. Schwartz section, as far as I recall, 5. I forgot. 5.1. That is much easier to understand than Peskin and Schrader. My derivation is slightly different from the Schwartz, but essentially the same. Oh, okay. Now the where did I? Yeah, section 5 is okay. So no question mark. Schwartz section 5 is much easier than Peskin Schroeder of this section. 4 point, I forgot, 3 in Peskin Schroeder. Anyway. So now, we consider so S initial and final. Okay. So there is a time at the infinity future. The final state is just plane wave solution with that I call it the final state, and the initial state is past infinity, minus infinity. T is the minus infinity is the initial state, and they are involved in the system, and there is some scattering appear here, but there's some interaction appear here, and of course this kind of the probability is indeed given by S, I call it Fi, which is F and S and I. And we know that this S should be unitary operator, because time evolution is indeed governed by unitary operator. So the S should be obey this kind of property, unitarity. And this SFI will give you, so the probability is is proportional to SFI squared. Okay? So that's the probability of this interaction happen is SFI squared. Okay? So that's the situation we'll consider. And now, suppose that so we would like to see that this guy. So why unitarity means conservation of the probability is that suppose we start with the Ni, start with psi, which is a state, which is a linear combination of n and n and n. So n are the basis of this system. Any basis is okay. And then we have the normalization is taken appropriately. So this is a normalization, so the psi square is equal to 1. This means equal to 1. Okay. This is a proper normalization. And we consider psi is involved by S matrix. At the end of the day, so it will become some states. Okay, some states in the future. And if the probability of this one is equal to square, you have to square it. Okay? So psi is involved to some states in a basis. But if you sum over n, this should be equal to 1. If you start with psi at the past infinity and involved by s, it should become some states in a basis. Okay? So therefore, if you sum over n, this should be equal to 1. That's the meaning of the probability of a conservation of probability. Okay? And this, let's see if this is the case. I don't know why. Sorry. It's too simple. Sorry, I wrote it very like a complicated way, even though it can be. So this is equal to psi s dagger s psi. Therefore, this is equal to 1. Sorry, it's super simple. Psi dagger, s dagger s is equal to 1, and I normalize psi is equal to 1. Okay, so therefore this is equal to 1. So therefore unitarity means that the conservation of the probability. So now where should I erase here? Okay, now so we consider the following form. So as matrix, so here, if there is sometimes so there is a process, it doesn't have anything. I becomes F without any interaction. I is equal to F. So this so we would like to remove this part, this kind of boring process. So therefore, is 1 means the delta Fi. Delta Fi means it doesn't have anything. There's no interaction occur. So past infinity and future infinity always during the same. You just separate this boring process, and then this is no trivial process. That's what we are going to consider. And then here, so since we consider this is a plane wave in the past infinity, and then future infinity is also their plane wave. So therefore, we consider the TFI will take the following form. So Breit-Wigner form we also decompose like this 1 plus IT. That's what I did when you try to get the Breit-Wigner form. Plus I times 2 pi. Actually here the property is any dimension. But anyway, so in my lecture note I wrote any dimension. So but any 4 delta 4 sum PF minus sum of PI. So this is the conservation of momentum. PF is the sum of all momentum in the future infinity. PI is the past momentum of the past infinity. And then we have the amplitude Fi. So that's the form I would expect. And then we would like to square it. So the probability is this SFI square. Yeah. And then we would like to focus on this part. Only this part. Only this part. I think instead of SFI, so I think I should change my lecture note. I think I'm using a notation of the N. So TFI square can be understood as the 2 pi 4 delta 4 and it's the same thing, and delta 4 same thing, and then MFI and square. Okay, so this is the form of TFI square. The lecture note is misleading. I will change it later. And we like to treat how to deal with these two delta functions. But we know that the delta function, if you have two delta functions, dx f of x, delta of x and delta of x, and if you integrate over, what's going to happen is this should be f0 and delta 0. Okay? Do you understand what I mean? So this integral only see one of the delta. Okay? So therefore this is equal to delta 0 dx f of x delta x. Do you agree? Do you agree with that? So you can just factor out delta 0. And we know delta 0, we already encountered many times, delta 4 0 is B volume times time, the volume of space-time. Okay? That we already learned many times. So therefore, we can just write down this guy. Sorry, I think so. This guy is as follows. This one is 2 pi of 4 delta 4 sum of pi. Times pi. So this is indeed equal to delta 4 0. Okay? Do you agree with that? So, and now, so as I mentioned here, so we would like to understand the probability of scattering per time and per volume. Okay? Per time and per volume. So therefore, PFI, P probability that I goes to F is indeed equal to, you have to divide it by B times T, which means that the 2 pi to the fourth delta 4 sum of PF minus sum of PI and then amplitude Fi. Okay. Are you following? I hope you guys are following. So here I already divided by B and T because it's unit time, unit volume. Okay. So now, so here, so we use the unitality, and then now we use this Lorentz invariance. We need to impose Lorentz invariance. And so we're interested in some differential probability, dp. Okay? And dp and the final state will be given in the the differential of moment at the final state. And then we know that the Lorentz invariant measure is always this form. F 2 times epsilon f product of f. This is final state. Okay. So this is Lorentz invariant measure. We already saw it, right? Many times. Do you remember? This is we learned it, right? I think is equal to E4P 2 pi to force delta P square minus n square, as far as I remember. Let me record my lecture note to explain. I explained this one somewhere in the lecture note. Okay, I think what I have written is roughly correct. Yeah. Times 2 pi, and then Heaviside function p naught is whatever. Yeah. So this is the case. So therefore, this is the Lorentz invariant measure. So right hand side manifestly Lorentz invariant, and left hand side therefore Lorentz invariant. So therefore, so if you try to take differential probability, so we have to use this guy. And combining with this one, we have the dp I minus f is essentially what we have is 2 pi. What was that? Yeah. Product of I is initial. 1 over 2 dpi. D pi. And d pi is so Lorentz invariant phase space. I mean, d pi is defined as the 2 pi and times this guy, product of f dq pf, pf, sorry, 2 pi q 2 So that is the this is called I mean often called Lorentz invariant phase space Lorentz invariant phase space. So this is the differential probability you have, and the exponential 2ei is kind of ad hoc here. Sorry, I'm just this 2ei is the same origin 2ef indeed. The exponential this guy is essentially written in Schwartz book. You can accept this 2ei is the same origin this 2ef, or maybe sorry. Essentially, what we need to do is f, s, I, and square, and then you need to normalize f, and then I, and this f and I will give you this ef and the ei. So therefore, you have to incorporate this 1 over e to ei into the differential probability. if you're interested in how to derive this this one, you can take a look at the Schwartz section 5. I'm trying to be very like a easier way to derive this one. In essence, this 2EI is the same origin to EF, so therefore you have to include it. So this is the form of the differential probability, and we just plug that one into the this form for scattering. But before then, we have to consider the interesting case is always interesting case is one particle is just stay into the multi-particle, so that is called decay. So I is one particle, so one particle to n particle, and in this case it's called decay. So as we saw in the resonance states, there's so-called lifetime and so on. So this decay rate is given by the gamma is equal to, so therefore 2 pi to 4 delta pi minus t, and then n square fi square to e, and product of d. Am I right? The correct thing? Okay, good. PS 2 pi. So this one. So this is decay rate. So this is differential probability of decay. Differential probability of decay 1 to n. Next is we are interested in, okay, let's erase here. 2 to n. So 2 to n means that there are two particles and just is. This is exactly what we are interested in. So there's target, and there's alpha particle and the scatter, right? Like this way. So this is exactly what we are interested in. So then the 2 to n, 2 to n, and this is time direction. So here 2 to n is the most interesting one. So therefore we need to include this 1 over b1 minus b2. So therefore, the cross section, the sigma, can be written as first we need to include what was it? So this denominator 2e1 and 2e2. And then m and I square d pi. Lorentz invariant phase factor. So that's the general form of the differential cross section, and from next lecture we will evaluate this guy. We will evaluate this guy. Evaluate by this by Feynman diagram technique. So as I mentioned, this. So starting from this asymmetric theory, we assume this unitarity, causality. Oh, sorry. Lorentz invariance, and then whatever. This kind of principle, we can just separate trivial interaction to non-trivial interaction, and if you impose the Lorentz invariance, we can just relate S matrix square and then differential cross section. So that's how you relate S matrix and cross section. Okay, so this is the general formula for 2 to n scattering. And then from next lecture, I think you will learn how to evaluate this matrix M. Any question at this moment? Okay. Now, so we just recall that the, as I mentioned, so in here, this B is a velocity, and if you go to the center of mass plane, center of mass plane frame, so therefore Bi minus B2, as I mentioned, this is equal to, Bi and B2 should be the, like in the center mass is the opposite direction, right? So therefore, and then Bi is, by definition, it should be P1 divided by E1, then minus P2 divided by E2. But however, so we know that the direction of P1 is just right opposite of P2. So therefore, if you take absolute value, then it should be plus. Okay? Do you understand? Is it okay? Are you guys okay? So B1, P1 and P2 are totally opposite. And we assume P1 plus P2 is equal to 0. Okay? Okay. Is it okay? So therefore, this is equal to P I. I can be both center of mass. Oh, sorry. So 1 over E1 plus 1 over E2. And this is equal to I. And this times, times. And we know this guy, E1 plus E2 is the center mass energy. Okay? Energy, total energy at the center of mass frame. Okay? So therefore, this is equal to E center of mass. Let me erase. So center of mass frame means that the P1 plus P2 is equal to 0. And this is equal to Pi center of mass E1. Okay. Now we will simplify the situation a little bit more. So therefore, you can just plug this one into there. I like to keep this part. So now, we will simplify our situation a little bit more. 2 to 2. So the situation is something like this one. One particle and then 2 particle is going to P1, P2 goes to P3 and P4. Okay? So we would like to understand this kind of situation. in center of mass prime. Okay. And so since we are interested, as I mentioned, so we are interested in d sigma and d omega. Okay. So we will look evaluate this one. So the question is how to relate this d omega and this Lorentz invariant phase space. So what is the relation in this process and differential d omega? So that can be easily seen that the omega, this guy, d pi, sorry, d pi is 2 pi to the 4th sum of p, and then so now it is center of mass plane. So therefore p1 plus p2 should be equal to 0, and the p3 plus p4 should be 0. Okay, so the momentum conservation, because of the momentum conservation. So therefore, this Lorentz invariant phase space, I have written at least this part, but this part should be something like this one: d cubed pf 2 pi to the 3 over 2e3 cubed to. So only one of them, because I mean we already know that the dp3 is equal to dp4. Okay, so we can ignore the one of them. Okay. I don't know why I remember. So then we can just. I don't know why I just write down like this. Oh, sorry, I shouldn't erase this one. And this is equal to 1/16 pi square. So here 2 pi to the 4th, and you have a 2 pi to the cube and 2 pi to the cube. So therefore, and 2 here and 2 here, what's left is 16 times pi square, and the omega and dpf. So here dpf is the radial direction. So this is the Cartesian coordinate, and this is the spherical coordinate. Do you understand what I mean? So here dp pf1, pf2, pf3, and then radius here. Here you have take the radius is the pf, radius is pf, and the omega is essentially d omega is equal to sine theta d phi, as far as I remember. Is it okay? Am I correct? I don't remember. The phi is this direction. Sorry, phi is this direction, and theta is this direction. This is spherical coordinate, and the omega is really the angular part of the spherical coordinate, and pf is the radius part. Okay. And now, what's left is the pf square, radius one, and then e3, e4. And this delta function, it just reduces to the energy conservation. Because I mean it's too trivial. I mean the spatial part is the momentum conservation too trivial, because when you go to center of mass, P1 plus P2 equals 0, P3 equals P4 equals 0. We already impose that by ignoring dp3 and dp4, ignoring. So therefore, spatial part I already use the delta function. Do you understand what I mean? Essentially, you have dp3 and maybe strictly speaking, this is a case. Strictly speaking, Lorentz invariant measure. So it's a finite product of finite state. But if you impose delta function p1 plus p2 equal to 0, p3 equal to p4 equal to 0, so therefore one of them will be gone. Okay, so then I call it that one is P F. Okay, so this is, and what's left is only delta function at the time direction, a time component. And now, so we will use the following trick that so we just following trick that the x, so x is equal to so dx and def, you just do the change of variable. And this is equal to, so note that the E3 is equal to M3 square plus, square, PF square, and E4 square is M4 square plus PF square. So therefore it's a function of PF. E3 and E4 are function of PF. So therefore it makes sense. E3 and E4 derivative makes sense. So therefore this is equal to PF E3 plus IU. Okay. Which one should be erased? This so then, so we know that I put delta f of x, correct me if I'm wrong, is 1 over f prime of x, and then like this way? Am I correct? Am I correct? Do you remember? Sorry, thank you very much. Okay. See you. Thank you very much. So therefore, so we use this, we apply the same thing here. Same thing here. So therefore then here, and this is equal to So now, so you just apply this rule into here. What you get is essentially equal to so this guy. So in the center prime, so this E center E3 and E4 will cancel with this E3 and E4. Okay. And this PF is cancelled with one of the PF, and what's left is E center of mass in the denominator, and then in the numerator you have an amplitude of the momentum, a spatial momentum. Okay, so now, so we have the relation between d pi and d omega, and we know, so that we just need to plug this one into here, and we know the b1 minus b2 is this guy, and then d pi is this guy. So therefore, let's write down d sigma is equal to 1 over. So let's write down from the what was it? Oh, here. It's 2e1, 2e2. And now, so we plug this one into here. So what should we get is pi. And then E center of mass E1 times E2. So that's this B1 minus B2 part. And now we plug in m square. So I plug this one into here, so therefore this is Pf. And then 2 pi square, 4 times E center of mass, and d omega mfi square d omega. Do you agree? Do you agree with that? Now, so we cancel E1 and E2. What's left is the 64 pi square E center of mass square over 1 Pf, Pi, and amplitude of the momentum, and mfi square times of d omega. So therefore, okay, I think I just write down d sigma d omega center of mass is equal to this guy. Okay. So if the mass of the two particles here, so all mass are the same. If all mass are the same, then we know that the Pi is equal to Pf. Okay. Okay. So, of course, so we have energy conservation, and I must have written somewhere. Okay. So here, so energy depends on mass. If they have the same mass, P3 and P4, the energy E3 and E4 are the same. And likewise, E1 is equal to E2 equal to E3 equal to E4. So therefore, the Pf and Pi should be equal. So therefore, the amplitude is significantly simplified. And this is equal to mfi square 64 pi square E center of mass. So that's what's happening in the 2-2 scattering process with same mass and at the center of mass. Any question at this moment? Are you guys following? I hope you guys following. Okay, so unfortunately I'm running out of time. So next time I will briefly talk about the consequence of this unitality. This consequence of unitality, and that unitality will tell us a so-called optical theorem. I think, did you guys learn the optical theorem in quantum mechanics? Okay. Okay, so Fudan education is not bad in that case. So unitarity optical theorem. So next time I will briefly talk about the relation, the consequence of unitarity. Optical theorem can be derived from unitarity of S matrix. And then also I will talk about the how to evaluate MFI in particular theory, which is called Yukawa theory. So next time, I briefly introduce this guy and then evaluation of MFI in particular theory. And we will gradually, so in coming weeks, we keep evaluating this MFI for many theories, essentially QED. Okay, so I think it's a good time to stop. So let's stop here, and then if you have questions, please tell me.